Hello there, this is Miss Nakayama. It is allergy season in Alabama. Today's lesson is 10.7 probability. It is the last lesson in our chapter on probability. So in this video, we are going to cover lots of examples. We're going to talk about computing empiric probability, theoretical probability. We're going to find the probability that an event will not occur. Then we're going to find the probability of one event or a second event happening, find the probability of one event and a second event happening. So, first off, you need to remember some basics about probability, and that is the lowest a probability can ever be is 0, and the closer it is to 0, then it is not going to happen. It's always between 0 and 1 or 0% and 100%. 0 means the probability is not going to happen. 100%, of course, or closer it is to 1, it absolutely is going to happen. But more importantly, unlike the last lesson, every answer to a probability question has to be between 0 and 1 or 0% and 100%. That percent sign is important. Leave it as a decimal or fraction and make sure it's always less than 1 and not negative, and you'll be good to go. All right, empirical probability, also known as experimental probability, okay? It is basically the observed number of times something happens over the total possible observations that you have, occurrences, okay? So look at this. It's observed over total in an experiment. So we have example 1, empirical probabilities. The data in the table are based on 100,000 U.S. women ages 40 to 50 who participated in mammography screening. Find the probability that a woman aged 40 to 50 has a positive mammogram. Okay, so if I want to know the probability of positive mammogram, then I'm going to find out how many women had a positive mammogram. So I'm going to add up 720, 6,944, and when I add that up, I get 7,664, and they told us up here that we had a total of 100,000 women. So the probability that a woman has a positive mammogram is going to be 7,664 over 100,000. Pay attention to how my lab math wants you to answer that question and round accordingly. But as a decimal, that would be your answer. All right, this is the same data, okay? So it says 2 out of 3. It's still example 1. It's like example 1, part A, B, C, but it's the same data. This time, okay, they're asking us among the women with breast cancer, find the probability of a positive mammogram. Okay, so the fact that they gave us this condition, or you might consider it they use the word among, they might use the word given, they might use the word of, but that makes it what we call a conditional probability, and it is written like this. And that says the probability that they have a positive mammogram given that they have breast cancer. So when you write it like that, and when you have that condition, that's just the second part of it, that changes the denominator. And now my denominator is not going to be total, but it's going to be the people with breast cancer. And so I'm only looking at this part of the table. So what is the total number of people? Of course, that's 800. How many of those have a positive mammogram? 720 out of 800, which is 0.9. So you got to pay attention to all the words. All right, last example in this same data. Okay, so it's still example 1. This time, among the women with positive mammograms, find the probability of having breast cancer. Though this is backwards basically of what we just did. So this is the given positive mammogram. So in this case, I'm looking at this. Okay. So those are the only people I'm looking at. What is the total of those people? 7,664. How many of them have breast cancer? 720. Pause for 1 second. So since our total was 7,664, that's going to be our denominator. How many of those have breast cancer? And that's going to be 720 out of our 7,664. And if you need a decimal, there's your decimal. Make sure you round properly according to MyLab Math. All right, so that was experimental or empirical probability. The next one we have is theoretical probability. And this, when you have an occurrence for which the outcome is uncertain, it's called an experiment. And the set of all possible outcomes of an experiment is the sample space of that experiment. And it is often denoted with the letter S. Any event in the sample space is E. Theoretical probability applies to those situations where you have equally likely outcomes, all of which are known. If you think about theoretical probability, if I flip a coin, what's the probability of getting heads? It is 1 out of 2 because there's one head and there's only 2 possible outcomes, heads or tails. Okay, so computing theoretical probability, I just said that. It's the number of outcomes, this is theoretical probability, the number of outcomes of the event E over the sample space, written like this. Okay, now most importantly, whatever it is you have, however many items are in your sample space, the sum of the probabilities of each event always has to add up to 1 because that's all the items, all the possible outcomes in your sample space. All right, let's look at this example 2, computing a theoretical probability. A die is rolled. Find the probability of getting a number greater than 4. So when you roll a die, you've got 1 through 6. How many of those numbers are greater than 4? 5 and 6. So the probability of a number greater than 4 would be 2 out of 6, which becomes 1/3. So I think sometimes they want it more as a fraction, but obviously that would be 0.33 if you need to round accordingly. Okay, another important concept you need to know is the probability of an event not occurring, and that is equal to 1 minus the probability that it will occur. Okay, so this is the formula for it. Probability of not an event is equal to 1 minus the probability of an event. And sometimes it's just easier, or we can figure this out more easily than we can figure out the not E happening. So look at this example. Okay, if one person is randomly selected from the world population represented by the figure, find the probability that the person does not live in North America. Express probability as a simplified fraction and as a decimal rounded to the nearest thousandth. So I want the probability that the person does not live in North America. That little squiggly symbol is the not. Okay. And that's equal to 1 minus the probability of people living in North America. So, of course, you could go add up all of the other ones, or you could just say 1 minus, how many live in North America. So, I'm going to have 1 minus, how many in North America? 550. And what's my total world population? Well, I have to add all those up. And when I do, I get 7,000 million. And so that's going to be my denominator. And when I put that in my calculator, I didn't give that as a simplified fraction. I only gave it to you as a decimal. So if you want to give me that simplified fraction, I'll give you a piece of candy. All right, moving on. Probabilities with mutually exclusive events. So if it's impossible for 2 events to happen at the same time, they are said to be mutually exclusive. A good example, you cannot get an A and a B in my class. You will either get an A or a B, but you can't get both. So how do you write that? The probability of A or B, that's a key word, is you just add the probabilities. Using set notation, you need to be familiar with that. Okay, or is this symbol right here is the union, and it's one that's either one. But when you're thinking of or possibility, you got to know to add the 2 probabilities. For example, if you roll a single-sided die, what is the probability of getting either a 4 or a 5? So the probability of a 4 or 5 is equal to the probability of 4 plus the probability of 5. I can't get a 4 and a 5 at the same time when I roll the die one time. So what's the probability of a 4? There's 1 4 out of 6 sides, and the probability of 5 is 1 out of 6. So when I add that, I get 2 6, which is, of course, 1/3. All right. Now, you have to talk about, well, what if they're not mutually exclusive? And if two events are not mutually exclusive, then you have to think about the overlap and subtract that overlap. So this one is probably a more important formula to remember, because if you remember this one more than the other one, if they're mutually exclusive, then the probability of A and B is 0. So if you remember this formula, you don't really need to worry about the one I just showed you. But let's keep going. All right. If one person is randomly selected from the population represented in the table, find the probability the person is married or female. So if I want probability of married or female, I'm going to find the probability of married plus the probability of female minus the probability of married and female. So how many are married? Well, I just told you that. Okay, it tells you right here. There's 130 out of the total of this many people. So 130 over 242. How many are females? Well, how many total females do I have? I have 124. So that's 124 out of 242. And then how many are married and female? Married and female would be 65. So this last number is 65 over 242, which equals 189 over 242. And as a decimal is 0.781. We usually don't put decimals fewer than 3 places because if you were to write it as a percent, that takes the percent out to the tenths place. Okay, continuing example 5, same set of data, just asking a different question from the data. Okay, this time we're going to find the probability that the person is divorced or widowed. Okay, so similarly, and y'all, when you take your lesson check, if you'll write this out, it gives you some partial credit. If you just give me an answer, I can't give you any partial credit. Probability of divorced or widowed is the probability of divorced plus the probability of widowed minus the probability of divorced and widowed. So probability, I didn't mean to do that. Probability of divorced, where's my divorce? This is how many people are divorced. 24, this is my total people, 242. Probability of widowed. Widowed is right here. So that's going to be plus 14 out of 242. How many are divorced and widowed? Well, clearly they're none of them. So that is 0 out of 242. And that gives me 38 out of 242 or 0.157, which I didn't mean to do that. There it is. Okay. All right. Now we have probabilities with independent events. Two events are independent if the occurrence of either of them has no effect on the probability of the other. And the probability of independent events is an and before we had an or, and it is the probability of A times the probability of B. So or means we're going to add the probabilities, and means we're going to multiply them. So in this particular case, last example, find the probability of a family having 4 boys in a row. Well, that's the probability of a boy and a boy and a boy and a boy, which sometimes is written like that. So that's the probability of a boy times the probability of a boy times probability. Those are independent events. If you have a boy, then it has no effect on whether or not the next one's going to be a boy. So that is just 1/2 times 1/2 times 1/2 times 1/2, which is 1/16. Okay? Now, the last thing I want to leave you with before you go, some of your questions will deal with cards, and I have found lately that a lot of students don't play many cards and don't know what's in a deck of cards. So, to refresh your memory, or to let you know if you don't already, you need to make sure you know this about cards. There are 52 cards in a standard deck. You have 4 suits. The suits are spades, hearts, clubs, and diamonds. Spades and clubs are black. Diamonds and hearts are red. And you have 13 cards per suit. And those range from ace to 10, jack, queen, king. So you need to be familiar with that information if you're not already, so you can answer the questions successfully. Thank you so much for watching, and you'll have a great day.